Hello everyone, welcome to the lecture number 19 of week 4. We were supposed to start moment area method today, but then again I thought since the equations of elastic line that we derived in first lecture of this week is very important, and you will come across this equation many times in your in not only in structural mechanics, in other engineering courses as well. So let us spend some more time on that equation and explore that to other problems using direct integration method. Okay, so today we'll address 2-3 problems using the equation of elastic line and direct integration method. Okay, the first problem that we do is this one. Is again a simply supported beam, but now the distribution of load is not uniform, it is triangular distributed load, and intensity of this load, when I say Q, the intensity of this load Q means at this point it is Q and it is linearly varying, and at point A it is 0. So what we have to do is we need to find out the slope and deflection at slope at point A and B, and deflection, what is the profile of deflection using direct integration technique. Now if you remember, the equation that we have is d2y dx2, that was the equation for elastic line m by ei. Mx is a function of x. Okay, so first we need to find out what is the expression of the bending moment mx. Let us assume for this beam E and I both are constant, both are uniform across the length. Okay, now so first we need to find out the support reactions. We already discussed how to find support reaction by drawing free body diagram of the entire structure. So I am not going to find out the support reaction once again. And if we draw the free body diagram like this, it is By and then Ay and horizontal reaction Ax. Horizontal reaction will be 0 in this case. So we get Ax is equal to 0, Ay is equal to QL by 6, and By is equal to QL by 3. If you sum them, Ay plus By will give you the total load. Total load is half into this length into intensity Q. So these are the support reactions. We know how to determine these support reactions, right? Okay. Now let us find out the bending moment expression for bending moment. In order to do that, let's take a section at a distance x from A. So and draw the free body diagram of that section. So free body diagram will be, the intensity of load will be Ay here, and then externally applied load, which is linearly varying, and then support shear force Vx, and then moment Mx. Okay, Ax and Fx here are not shown because they are 0 here. Now if this distance is x, so if this is Q, then at a distance x, the intensity, if at a distance L intensity is Q, then at a distance x, intensity of this load will be Qx by L. Okay, Qx by L. Now this is the free body diagram of section X, of section, say if it is section 1-1, if this is section 1-1, then it is free body diagram of section 1-1, free body diagram of 1-1. Okay. Now from this free body diagram, if we take moment about A, which is equal to 0, and then if we take moment about A is equal to 0. So, sorry, moment about, say not A, say moment about this point, if you take is equal to 0, summation of moment at x is equal to 0, then the forces will contribute is Ay and the moments mx and the externally applied load here, and the expression will be, now mx is anticlockwise, so it is negative mx, and then the moment due to Ay will be clockwise, this is Ay into x, and then moment due to externally applied load will be again anticlockwise, and this will be minus the area is half into qx by L into x. This is the area of this triangle, and the centroid of this triangle will be at a distance x by 3 from this. So, into x by 3, this will be the moment due to this load. So, that is equal to 0, and this will give us mx is equal to q L by 6 x. Ay is equal to already determined QL by 6 minus Qx cube by 6 L. So, this will be the expression for mx. Okay. Now, this expression needs to be substituted in this equation and then integrate it. Let us do that. If we substitute this expression in this equation, what we have is this. Yes. So, we have d2y dx2 is equal to minus mx by ei. So, this will give us ei d2y dx2 is equal to minus of this expression, and this will be minus ql by 6x plus qx cube by 6l. Now, this needs to be integrated. So, if we integrate first time, dy dx becomes minus ql by 12 x square plus qx to the power 4 by 24l plus c1. Okay. And then again integrate it second time, this will become minus ql by 36 x cube plus q x to the power 5 by 120 L plus C1 x plus C2. Now, we have two constants C1 and C2. These two constants need to be determined. So, we need two boundary conditions. What are the boundary conditions we have? The boundary conditions are at x is equal to 0 means at A y is equal to 0, and x is equal to b at x is equal to L means at b again y is equal to 0. So, boundary conditions we have are at x is equal to y at x is equal to 0 is equal to 0, and y at x is equal to L is equal to 0. And if you substitute these two boundary conditions, then and evaluate C1 and C2, what we get is C1 is equal to 7 q L cube by 360. I leave it to you, please check that. C2 is equal to 0. So, this is C1 and this is C2. So, if you substitute that, if you substitute this C1 and C2 in this expression, so final expression of y we get as this. Y is equal to y, let's write as a function of x. Y as a function of x is equal to qx by 360 L EI 7 L to the power 4 minus 10 L square x square plus 3x to the power 4. So, this is the expression of y as a function of x. Now, let us find out where y will be maximum, where y is equal to maximum. How do you get? Dy dx is equal to 0, slope will be 0, and if you get dy dx is equal to 0, this give us x is equal to 0.519 L, means at x is equal to this value 0.519 L, y will be maximum. And if you evaluate entire y at x is equal to this, then we get y max or delta max is equal to, which is equal to y at 0.519 L is equal to 0.00652. Please check these values. Do not take these whatever results I am writing here, do not take them for granted. Please check yourself whether these results are correct or not. So, this is the maximum y value for this problem. Okay. Now, let us do the same problem again using direct integration method, but using a different form of this equation. If you remember, the another form of these equations, the same equation of velocity, there are two other forms of the same equation. One form was d4y dx4 ei, that is equal to q, okay, where q is the intensity of the load at that particular point. Okay. Now, when you write this expression, actual expression was this, right? d2y dx2 is equal to minus mx. Actual expression was this. From this expression we derived this. When we write this expression, it is assumed that E and I are constant, are uniform across the length. They are not function of x. But if they are function of x, then you cannot write this expression like this. And what you have to write is, then that expression becomes d2y d2 dx2 ei of d2y dx2 is equal to minus m. Okay. Your expression becomes, because if ei are the function of x, but if they are constant uniform throughout the length, you can take it out and finally you will get it. But as far as this problem is concerned, ei are constant, so we will be using this. But make sure whenever any problem you address by using direct integration method or any other method, check what are the information given about the material properties. Okay. Now, material and geometric properties. So, let us do the same example once again by using the other form of the equation of elastic curve. Okay, great. Now, so again let us not write the so if we take at L, this is Q, at any point x, if we take any section x here at a distance x, at any point x, the intensity of the load will be Q by L into x. Okay. So, when I write this expression d4y dx4 is equal to Q ei, this Q is actually the intensity of the load at that point. So, in this case it will be Qx by L. So, this is the equation, right. So, this is the intensity of the load at this point, So, intensity of the load also changes as per this equation. Q is Q is this value, but at that particular point intensity of the load will be Qx by L. So, this is varying across the length, but if Q is for uniformly distributed load, this will be constant, right. Now, so once we have this expression, let's differentiate it. Now, if we differentiate it first time, then it becomes Ey d cube dx3 is equal to Qx square by 2L plus C1, and then if you do it next time, second time, Ei d2y dx2, this becomes Qx cube by 6L plus C1x plus C2, one more constant, then do it second time, the third time, then this becomes dy dx is equal to Qx to the power 4 24L plus C1 x square by 2 plus C2x plus C3, one more constant, and then finally do it from slope, get the final deflection, and becomes, this will be Ei, this becomes Ei of y is a function of x, this becomes Q x to the power 5 by 120L plus C1 x cube by 6, then plus C2 x square by 2 plus C3x plus C4. So, we have now one constant C1, then C2, C3 and C4, 4 constant, which is justified because the equation was fourth order equation. So, we have 4 constants. Then let us see how many boundary conditions we have. One of the 2 boundary condition is obvious. One is here deflection is 0 here and deflection is 0 here. So, 2 boundary conditions, one is y is equal to y at x is equal to 0 is equal to 0, and then y at x is equal to L, that is equal to 0. These are 2 obvious boundary conditions. Now, let us see any other boundary conditions we have. We do have other 2 boundary conditions. You see, these are simply supported, these are hinge. Here what is the pin support and the roller support, they do not have any constraint against rotation. So, moment at this point and this point will be 0. Now, if moment is 0, and if you remember this equation, if the moment is 0 at any point, then curvature has to be 0, right. So, d2y dx2 has to be 0. So, what other 2 boundary condition we have? d2y dx2 at x is equal to 0 is equal to 0, and then d2y dx2 at x is equal to L is equal to 0. So, these 2 comes from the fact that deflection at this point and this point is 0. These 2 comes from the fact that moment at this point and these points are 0. Okay. Now, you will see when in any boundary value problem is where the equations, governing equations are given and along with some boundary conditions are given. There are 2 kinds of boundary conditions we can have. One boundary condition is directly applied on the primary variable. For instance, here the variable is deflection. Those boundary conditions are called essential boundary condition or Dirichlet boundary condition, and another boundary conditions are specified on forces. For instance, moments at 0 at a given point or moments are specified at a certain point. Those boundary conditions are called Neumann boundary condition or natural boundary conditions. So, here 2 different kinds of boundary conditions are given, right. Now, if you use these 4 boundary conditions and compute the 4 constants C1, C2, C3, C4, then final value will be C1 is equal to minus QL by 6, C2 is equal to 0, C3 is equal to 7 QL cube by 360 and C4 is equal to 0. So, again if you substitute C1, C2, C3, C4, in the final expression, in this expression, then the expression of y will be y again, let us write as a function of x, q x by 360 L ei 7 L to the power 4 minus 10 L square x square plus 3 x to the power 4. This expression is same as the expression we obtained just now. So, again you take dy dx, then rest of the thing is same, dy dx is equal to 0, where at y is equal to y max, and this will give you x is equal to 0.5519, just like the previous case, and final y max is equal to 0.00652 q L to the power 4 by ei. Again, please do not take these results for granted, please verify yourself. Okay. So, the point is there are three forms available of the equation of elastic curve. Depending on the equation, you have to decide which form to be used. Okay. But any form you use, essentially you will end up with the same solution. Okay. Now, let us do one more example. This example is in the last class I briefly talked about this example, but it will be better if we solve it here itself. The example is this, again a simply supported beam, which is a concentrated load acting at the at a distance a from point at a distance, these are a and b. This distance is a and this distance is b. This distance is b, if it is not properly visible. Okay, what we need to find out? We need to find out the expression for y. Okay. Now, you see this problem we can expression of what would be the bending moment and shear force diagram. If you remember, the bending moment diagram for this problem was like this. Let us not write the shear force diagram right now, because we do not need it, and this expression was P A B by L. This value was P A B by L. This was the bending moment diagram. If you remember, we drew this bending moment diagram. So, expression for bending moment between A to C and between C to B, they are different. So, when you use that equation, that del 2, when we use this expression that d2y dx2 is equal to minus m by ei. So, expression of m are different for this part and different for this part. So, we need to consider, we need to divide the problem into two sub problem, one for this and another for this, with the condition at point C you have sufficient level of continuity. So, let us do that. So, take in the first case, so this is for x which is between 0 to a, and then it is x between a to L. Okay. And the expression for bending moment is, bending moment here is mx is p into b by L x. Please verify this yourself. And for this, the expression for bending moment is p b by L into x minus p into x minus a. Okay. So, at x is equal to, let us see whether they are consistent or not. At x is equal to 0, bending moment will be 0 here, this is consistent. At x is equal to b, bending moment should be 0 here. Please substitute that at x is equal to L, bending moment should be 0. So, x is equal to L, if you substitute, then you get this value is also 0. At x is equal to a, they should have the same value. X is equal to a, it is P A B by L, x is equal to a, this is also P A B by L. Okay. So, then apply this expression, d2y dx2 is equal to minus ei. So, ei d2y dx2 is equal to minus Pb by L into x. Okay. So, integrate it first time, dy dx is equal to minus Pb by L into x square by 2 plus C1, and then second time y is equal to minus PB by 12 into x cube by 6 plus C1x plus C2. Okay. This is 3, sorry, this is 3. Okay. Now, let us do the same thing for this part. So, this is EI d2y dx2 is equal to minus of this minus PB by L into x plus P into x minus A. So, EI integrated first time dy dx becomes minus P B by L x square by 2 plus P into x minus A square by 2 plus C3. Let us write is C3 here because C1, C2 we have used for the other part. Ui y is equal to minus PB by 2L x cube by 3 plus P into x minus A cube by 6 plus C3x plus C4. So, we have 1 constant, 2 constant, 3 and C4. We have 4 constants, that this 4 constant needs to be determined. Okay. Now, what are the boundary conditions we have now? One obvious boundary condition is at two obvious boundary condition at x is equal to A, y is equal to 0, at x is equal to B, y is equal to 0. So, for this case, for this part, the boundary conditions are x is equal to x, y is equal to 0 is equal to 0. Okay. And for this part, boundary condition is y is equal to y at 0 is equal to 0. Remember, if you y at L is equal to 0, this expression will not satisfy, because this expression is only valid between A and C. Similarly, y at x is equal to 0 will not be satisfied in this equation, because this equation is only valid between C and B. So, this boundary condition belongs to this part, this condition belongs to this part. Now, other than these two boundary conditions, there are two other equations, two other conditions needs to be satisfied. These are the continuity at C. You see, when I write this expression, that d2y dx2 is equal to 0, it is assumed that y is differentiable up to second order at least. If not, then this equation itself is not valid. So, if y has to be differentiable up to second order, then the y should be continuous at C and its derivative also should be continuous at C. So, other two boundary conditions we have, which is at this point, that if we compute, suppose if we say this is y1, if we y1 and this is y2, this expression is y1 and this expression is y2, then the boundary conditions are that y1 at A should be equal to y2 at A. So, if we evaluate the deflection of the beam at point A, at point C, which is at x is equal to A, from this expression, and deflection at point C from this expression, they should be same. And the next boundary condition is y1 dash at A is equal to y2 dash at A. Means it is y1 dash is dy1 dx and y2 dash is dy2 dx. So, these are another two boundary conditions. So, total 4 boundary conditions what we have is, one is y1 x is equal to 0 and y2 L is equal to 0 at B is equal to 0, and continuity equation y1 A should be equal to y2 at A and dy1 dx at A should be equal to dy2 dx at A. So, these are 4 boundary conditions, and if you substitute these 4 boundary condition, what you get is, you get it C2 is equal to 0, C2 is equal to 0, then C1 is equal to C3 is equal to PB L square minus B square by 6L, and again C4 is equal to 0. So, final expression you will get is this. Final expression you will get is E y is equal to P b x by 6L L square minus B square minus x square, and this is for x less than equal to a 0, and E I y is equal to P b x by 6L L square minus B square minus x square plus P x minus a whole cube by 6, and this is for x less than equal to L equal to a. So, these are the solution. Okay. Again, you can differentiate at y to get the point where y is maximum. Okay. So, like this you can apply this equation to many other problems, with many other boundary conditions. You try yourself. All the example that we have done here, we assume that dI is constant, but as I said, dI may not be constant, and if they are not, then what happens to this equation and how this equation needs to be integrated. Please do it yourself, and if you see any book, there are many examples given. Okay. So, this equation, the equation of elastic curve, is very important, not only for this course. You will see in future there are many occasions you will come across this equation, and many practical problems these equations are being used. Okay. So, what we do next is we study two other methods. One is moment area method and conjugate beam method for determining deflection of statically determinate beam. But we will see that the premise of these methods are these equations. Okay. So, any confusion, there should not be any confusion as far as derivation and application of these equations are concerned. Okay, then see you in the next class, where we will discuss the moment area method for determination of statically determinate beams. Okay, thank you.